In this first lesson we will be taking a look at some of the most common options of Visual MINTEQ. Mainly these are the options that you see here on the main page of the program that opens when you double click the Visual MINTEQ icon. So you get into this main menu and we can see what we have here. If we start from the left, we have pH here. There are three different options for setting the pH, and this calculated from mass balance option is the first one that you see. But if you click here, you see a couple of other options. Basically, the most common of these options, I would say, is fixed at. This means that basically you know the pH, it has been measured, or you have estimated a pH. For example, let's say that the pH of your water is 6.4. So then we just enter this figure into this text box there. There are two other options. We have these calculated from mass balance option and calculated from mass and charge balance option. We will see in a later lesson how these two different calculated options work. But right now we can settle for this. We fix the pH, we know it is 6.4. We then go on to the ionic strength. This also has different options. Either you know what it is, so you fix it at some value. For example, 0.001 is the default value, and the unit of this is moles per liter. Let's say if it's 0.01, then you just change it to this, and then you go on. I think in most cases you don't know what the ionic strength is, so you let the program calculate it for you. So then we will stick to this option here. Okay, so that was pH, ionic strength. We can go on to this lower part of this menu where you add components. And what is components? Well, components in a general sense is a building block of a chemical reaction, but you can most sort of practically think of it as a total concentration of something, of an element, for example, that you have in the water. If you click here, you find a lot of different components we have in the database. And the general rule is that there is at least one component for every element. So for example, for calcium, which we have here, Ca+2, we have just one component. So if we add calcium to one problem here, we just click calcium here, and then we need to supply a total concentration. And what this is basically this, you can think of it as a total concentration of calcium that you measure in the water. We don't know at this stage if this calcium is really free calcium ions or if it's bound to something in the water, if it's a complex bound to a ligand, for example. Okay, so if we have measured calcium in a particular water sample, we enter the concentration here, and then before we do that we need to decide what unit we have for calcium. What unit did we get the calcium results in? And to change that, you go on to the right hand part of the menu. Here is where you change the concentration unit. You have a number of different choices. Most commonly, maybe you have measured calcium in the concentration unit of milligrams per liter. So then we choose milligrams per liter here, and then we enter the total concentration of calcium. So let's say we know that we have 10 milligrams of calcium per liter. So then we just add 10 here, and then we add calcium to a list. So then we have added calcium to the problem with this particular concentration. Before we move on with these components, we can just a few more comments on the concentration units here. You can see here that the default unit was molal, which is moles per kilogram. In fact, this is a thermodynamically correct concentration unit. But in most cases, for most natural waters, you have density of water that is very close to 1 kilograms per liter. And this means that 1 molal is the same as 1 mole per liter. So you can think of this as moles per liter. And millimolal is millimole per liter, and micromolal is micromole per liter. Here you also can set the temperature. Okay, so we had now specified calcium, 10 milligrams per liter. At any time when we add components to a new problem, you can check what we have added so far. So if we go to the list, we can click View Edit List here, and then you see our calcium there in this concentration, 10 milligrams per liter that we specified. We can also see that we have hydrogen ions in the problem. Unfortunately, it is possible to delete the hydrogen ions, but please never do that, because the hydrogen ions are always there whenever you deal with natural waters. So they should be there. The total concentration as given here is 0, and this is because we have fixed the hydrogen ion concentration, or more correctly the activity, because we specified a pH value. So then the relevant information for the hydrogen ions are actually not found in this particular table, but in another table, which we see here, the list of fixed species. So if we click there, here we find our hydrogen ions, and it has a specified fixed log activity of -6.4, which is the same as pH 6.4. So there we have our hydrogen ions defined. Okay, let's get back to the main menu now. So we started, you can say, with specifying water chemical composition. And let's suppose that we have a water that contains calcium ions and that also contains sulfate ions. It's sort of very simple calcium sulfate water. So of course then we need also to find sulfate in the list here. So we click this combo box and we find sulfate, and in fact we find sulfate here, SO4 -2. So we click sulfate, and then let's suppose that we have 20 milligrams per liter. So we add that to the problem. So now we have water that has this pH 6.4, we have 10 milligrams per liter of calcium, we have 20 milligrams per liter of sulfate. There are a few more things about the component list that you should know. I mentioned that for many elements there is one component for every element, but there are exceptions, and for sulfate is one example. You can see sulfate is here, but then we have other forms of sulfur. We have, for example, sulfite, SO3 2-, and we can also find further up the list here sulfide, which is present as HS-1 as a component. So we have 3 different components for the element sulfur. The reason is that these have different oxidation states. So basically you have one component for every oxidation state of an element. And in addition to that, there are actually additional components. So for sulfate, you can actually give sulfate as a sulfur. So if we choose this component, where you see S is for sulfur and sulfate within parentheses, this means that we can allow the concentration to be given in terms of milligrams per liter of sulfur instead. And that's a different thing, because if we measure sulfur and sulfate, it will not be the same molar concentration when you have the same concentration in terms of mass, because these forms of sulfur and sulfate, have different molar weights. And that is also the reason why there are 2 different forms of sulfate in the table here. You choose the one that is relevant for the concentration unit that was given in your analytical report. That is the one that you should choose. So we've done that now. We have 20 milligrams per liter of sulfate, and we have this problem. Well, actually, we can see what we get out of this MINTEQ program when we run it at this stage. So we run MINTEQ, we click here, run MINTEQ, and then we get these output tables, which consists of different menus. And this is the main output menu, where you, for example, if you look at in the upper left here, you see pH, of course, same as we defined. You can also see that the program has calculated the ionic strength, and again the unit is in moles per liter. To the right, here we have the charge balance. So the program has calculated the cation equivalent sum in the unit of equivalents per kilogram, which is again basically the same as equivalents per liter. And then the sum of anions in the same unit. And ideally, of course, these should be equal to one another, because then you have charge balance, and that we know, of course, that this is valid in all waters. The charge difference is an estimate of the error here between these two. So this is a good way of actually calculating the apparent charge balance error. You add everything you measured to the program, and you let the program calculate the charge difference. Down here you can see the different species that the program found in this water. So for example, we have free calcium ions, calcium 2+. The concentration here is in moles per liter now. And it also calculated the activity using the Davis activity correction equation. It's important to note that the output concentrations are always given in the unit moles per liter, irrespectively of what you had in your input. So if you had milligrams per liter in the input, you will still get all results in moles per liter. You see that calcium actually is not only present as calcium 2+, but also in a couple of other complexes that you can see here, calcium OH and calcium sulfate. And from the concentrations, it can be difficult to see. Well, you can see here clearly, of course, which ones that predominate, but there is also a special menu for that. So down here in the View Species Distribution page, you click there, you open a new menu, and here you see the percentages of calcium and sulfate that is distributed on these different aqueous species. So we can see here, for example, for calcium, that 96.6% of the calcium in the water is present as free calcium ions, and 3.4% as calcium sulfate. Okay, then we go back here. You might have noted at this stage that you can also export these results to Excel, and you can work with them more. So if I click here, I will open basically the same table here in Excel. Okay, get out of Excel here. Don't say this, and it disappears. Okay, so this was the main output menu. We looked at the species distribution page. We have a couple of more pages here, as you can see. First of all, we have the display saturation indices or indexes. So if you click here, you can see what different mineral phases that potentially can form with the different components that we have defined. And one such mineral phase is gypsum, because it consists of calcium and sulfate, which we defined. Water, of course, is always present, so we didn't need to add that as a component. And you see here that gypsum has a saturation index of -2.8. Now this saturation index is defined as the logarithm of the ion activity product minus the logarithm of the solubility constant. And when it's defined like this, it means that the negative values means that you have undersaturation, which is also clear from the color coding that you see down here. So this means that none of these minerals here, they can form in this water, and you have a large undersaturation, meaning that they are probably not present. They don't sort of determine the chemistry of this water, probably. Okay, so that was the saturation indexes. Equilibrated mass distribution here, the third menu. Here you will see you can get division here as to what extent these different components are dissolved in the water, if they are sorbed or if they are precipitated. And in this case it is very easy because we didn't define any adsorption reactions and no precipitation reactions either. So everything is dissolved in the water, and here you have the total dissolved concentrations, which basically are the same as the one that we entered on the input menu. It's just that then we used milligrams per liter, and now we have mole per liter here. So in this particular case, this table was not very interesting, but we will see in other problems that it will be interesting. But okay, this gave maybe hopefully gave you an overview of the different type of results to get when running a simple problem like this. We can now go back to the input menu, and of course there's a couple of more things I want to show you before we end this lesson. First of all, at any stage you can also save a copy of the input that you have done, like any other program, of course. So if you click Save Input Menu here, and then you enter something like, well, I don't know, I just add a few letters here. So this is our input menu, and then we can save it to the disk. So you can get these data later on if you do something else. That was the first thing. The second thing is that when you work with a program, and when you start over with a new program, it's important that you delete all the information from the previous problem. So therefore you should use this reset button. So clicking reset means that we get back to the sort of start state here. So we can start over with a new program without getting contaminated by the figures of the previous problem. And now of course we can open a new program. So if we can find our file that we saved, this is the one, we can open it and we get back the calcium and sulfate and so on that we got. Okay, thanks for now. That was lesson number 1.